happens, right, under no bias condition? Okay, under no bias condition, the Fermi levels are aligned. Okay, under forward bias condition, it shifts upward. Okay, right? Simple. Under forward bias condition, whatever you have on the n side, it shifts upward. Okay, all the energy bands, they shift upward because you are giving additional negative supply on n side, so the energy levels will start to rise. Okay, right? Okay, so here now under no bias condition, this is the situation. Okay, right? This finger indicates my energy level. Okay, in fact, that is the highest energy level of the valence band, which is this. Thumb finger indicates the Fermi level on p side. Okay, right? And then next, my index finger, I will indicate the Fermi level on n side. My thumb finger, I will indicate the lowest level of the conduction band on n side, which is actually EC. Okay. So now under no biased condition, this is the situation. Under forward biased, okay, the situation is like this, which we can see now. So, okay, now this is like, as I told you, this is like the space for water to flow, and this is like the amount of water that is available. Okay, represented, I have represented here by blue color. Remember it as water. Okay, right? So now under no bias, no water flow. Now if we keep on increasing, now the situation which you can see on the screen, the water, okay, this much level will start to flow. So there is current flow. Further, if we increase the, okay, further if we increase the forward voltage, if we increase the forward bias, then the current will keep on increasing. At this point, maximum current will flow. Okay, right? So it is like two pipes. One has water, another is empty. Now no water flow. Now water will start to flow. Okay, okay. Now no water flow. Water will start to flow. Maximum water will flow from one pipe to another pipe. Now if we further increase the forward bias, okay, then the water flow will reduce. Now the water flow will become minimum. Here onwards also the energy level will keep on shifting higher. Okay, but what happens is these bands, the EC and EV here, will start aligning with the EC and EV here. The EC and EV on the, okay, P side will start aligning with the EC and EV on N side. Then it will behave like an ordinary PN junction diode. Okay, right? So the characteristics of the device based on this will be, okay, first, this we have discussed. Reverse bias we have already discussed in the previous class. Okay, right? Now what about forward bias? The characteristics that we get, okay, will be like this. Okay, the characteristics that we get will be like this. Why we have the characteristics like this? We keep on increasing the forward bias, the current keeps on increasing until maximum current reaches. After maximum current reaches, the current will start reducing. Okay, right? So this is where maximum current is reached. Okay, after that the current will start reducing. Okay, right? So once again I am going back. First we are here. Okay, now we are here, the bands have aligned. Okay, maximum tunneling is possible. Now the bands slowly moving further upward. Okay, So there is only little space for flowing and it is reducing. Now current has now become minimum again. Okay. Afterwards, what happens? The ECEV on this side will start aligning with the ECEV on the other side. Okay. And then the current will start to flow similar to that what happens in an ordinary PN junction diode. Okay. So after that, it simply follows the characteristics of ordinary PN junction diode. Okay, right? Next, what we will do is we will see the various points on this graph. Okay, this particular point, see there is one peak here, there is one valley, you know, peak, mountain peak. Okay, this is like mountain shape, right? Mountain peak, then valley. So this point is called as peak point. This point is called as peak point. Okay. Next, the bottom most point here, this point. Okay. Okay. This point is called as the valley point. Okay. Peak point, valley point. Next, see in between peak point and valley point, now what is happening? Okay, something strange is happening. Okay, so first, from origin to peak point, from origin to peak point, it is behaving like a resistor. In fact, in the reverse bias also, it is behaving like a resistor, and a resistance of very small value, say 5 ohm. Okay, around 5 ohm, right? Because from this point to this point, when we gradually increase the voltage, the current is increasing. Okay. But after peak point, between peak point and valley point, what is happening? Although voltage is increasing, current is reducing. Okay. Now, say from this point to this point. Okay. Right. That is before peak point. Before peak point, what is the situation? The slope is positive. What is slope? You know very well. Dy by dx. In this case, y in place of y, you have current. In place of x, you have voltage. So di by dv. Okay, di by dv will give slope of a straight line. So before Vp, that is peak point, before the peak point, right? Sorry, before the peak point, then the resistance is actually okay positive because slope is positive. Actually, slope indicates conductance, right? Di by dv, current by voltage is conductance. You know, reciprocal of conductance in resistance. Anyway, right? When a value is negative, its reciprocal is also negative. 2, suppose minus 2, reciprocal of that minus 1 by 2, both are negative. Okay, so ultimately what I am trying to say is before the peak point, it is exhibiting positive resistance because di by dv, slope is positive, simple, slope is positive, so positive resistance. Next, between peak point and valley point, between peak point and valley point, what is happening? Okay, when voltage is increasing, current is reducing. Okay, right? So what does that mean? Negative. resistance because negative slope. Okay, negative slope. And after valley point, again voltage increases, current increases. Fine. So positive resistance. So let me shade this in between region as negative resistance. Okay, I will shade it as, say, I will name it as negative resistance. Okay, negative resistance region. It is known as negative resistance region. Next, we have discussed peak point. The corresponding voltage is called as this peak voltage Vp. Okay, corresponding current at peak point is known as peak current Ip. Next, corresponding voltage at valley point is known as Vv, valley voltage. Corresponding current, okay, at the valley point is known as IV, valley current. Okay. Now let us see the symbol of the, okay, tunnel diode. Okay. Now it is somewhat similar to ordinary PN junction diode, right? It is somewhat similar to ordinary PN junction diode, but the only difference is, okay, see, anywhere between peak point and valley point along the y-axis, for a given current value, you have 3 voltage values. For example, here, okay, when the current is somewhere here on the middle of the positive y-axis, the voltage can be less than Vp, greater than Vp, or here, this point, greater than Vv. For a given current, you can have 3 voltages, okay. So that is represented by 3, okay. That is represented, see, this is like 3 here. You know, 3, how we will write 3? You will write like this. So that is the symbol of the tunnel diode, okay. Just same, you have these terminals anode, you have the terminals cathode. Okay, clear? So you have understood the symbol of the, okay, tunnel diode. Okay, so this is about the tunnel diode. Any doubts so far? Okay, all of you, I expect you will watch the video. Okay, and you will, right, go through this, and any doubts you can ask. Now, if you see the characteristics of this, okay, basically, given a current value, you can easily shift the voltage. Okay, for example, you have current value here and voltage is here. You give a small trigger, then you can shift the voltage here and it will maintain that state. Okay, another trigger, right? So because of that, it is used in logic switching, right? And the negative resistance is primarily used in oscillations. Okay, so it is also used as oscillator. So the main applications of this particular tunnel diode will be, okay, logical switching. It is useful in logical switching and it is also useful in oscillators. Okay, right? So any doubts so far, whatever we have discussed? Okay, if no doubts, right, then we will go for the next topic, which is unijunction transistor. Okay. So from the name itself, you can understand that it has only one PN junction. Okay, it simply has only one PN junction. Okay. So first, let me construct. Okay, let me give you the construction of this particular device. Okay. So basically, what you have, okay, what you have first is you have an N region. Okay, you have an N region, and to that N region, an aluminum is alloyed on one side. Okay, right? So first of all, okay, let me label this. Okay, let me call it as N region. Okay, okay, I will write here. Okay, then to this N region, on one side, aluminum is alloyed. Okay, on one side, aluminum is alloyed. Okay, so this is aluminum. Aluminum acts as a p-type impurity. Okay, so N region, when aluminum is alloyed, okay, this p-type impurities they diffuse into N region. Okay, suppose N region is like, okay, let me give you one small example. Say -5. To -5, if you add 500, okay, then it becomes positive. So same logic to the N region, when aluminum is alloyed, a P region is formed. Okay, P region is formed. Anyway, first let me label this. Okay, so this one is aluminum. Okay, right. So because aluminum is p-type impurity, as a result, what is formed here? PN junction is formed. Okay, where the PN junction is formed here. Okay, right. Next, the device is ready. All you need to do is we need to give contacts. Okay, we need to give contacts. So basically, this device has three terminals. Okay, first, this is called as emitter. Okay, first terminal is called as emitter. You know very well, right? You represent emitter by E. Okay, and it has two base regions. See, transistor has emitter, base, collector, right? Which transistor? Bipolar junction transistor. This is uni-junction transistor. It has only emitter, base, right? No collector. But that particular base, okay, that particular base actually is two terminals. Okay, what do I mean by that? In fact, the device has total three terminals. First terminal is this emitter. Okay, then remaining two terminals both are base terminals. Remaining two terminals both are these base terminals. Okay, So this two terminals, both, okay, both these two terminals, both of them are the base terminals. The top terminal is base 2, okay. The top terminal is base 2, the bottom terminal is base 1, right? Now, if you see the equivalent circuit of this, okay, it is something similar to, you have a PN junction, okay, right? You have a PN junction and followed by one N region, okay, PN junction followed by N region. So the equivalent of this we can represent by a PN junction diode, okay, we can simply represent that by a PN junction diode, okay. What is it? Right? And then PN junction followed by two resistors. See, entire N region, every material has resistance. Okay, so the entire N region also has resistance, right? But we can now divide this into two regions. We can now divide this into two regions. One is, okay, above this particular diode, and then above the diode, this is PN junction. So it is equivalent to a PN junction diode, above the PN junction diode and below the PN junction diode. Okay. So I will represent by two resistors. Okay. I don't know how I will be able to draw the resistors. Okay. So this top terminal, okay. Let me complete the resistors. Okay. So please take this as resistor. Okay. Right. Next, same resistor. Okay. In fact, one more resistor. Okay. You have, in fact, one more resistor you have at the bottom. Okay, fine, right? So this is the equivalent of the, okay, unijunction transistor. This is the equivalent of the unijunction transistor. So this one obviously will be the emitter. The first terminal will be the emitter. Okay, right? So this is the emitter. Then this is base 2. Okay, this top terminal is base 2, right? Similar to this diagram which we have, okay, and this bottom is base 1, okay. Emitter base 2, base 1, because you have a PN junction, and then an N region you can view it as resistance. Okay, we'll continue in the next class from here. Okay, right. Any doubts, don't hesitate to contact me.